Welcome, Brad. The Lilla High Lecture Series. Brad, I know well. He did his undergrad studies in Pennsylvania to be a physicist initially, but then converted to becoming a bioengineer. He was actually working for 3 years after that. He thought he would do more imaging stuff, and he was in charge of the positron emission tomograph at the VA. In Minneapolis, so he was here for 3 years, so he knows his way around. And then he went to Boulder for 7 years, I believe, before Norman Alpert at the University of Vermont could attract him. Norman had was really an interesting person in that he founded the Department of Molecular Physiology and Biophysics. It was a small but feisty program that has a lot of, it was a really incubator for commercial successes, including Norm's own company, which was biotech, that his sons actually sold off for $1.2 billion.
Wow.
Yeah. So this is not the typical little company that you start to get a small business innovation grant. This is real business here. But Brad himself is a serial entrepreneur himself, had multiple companies, was very involved in ion optics in the beginning, wrote actually the source code that's still running on these machines. Actually, it's one of the reasons why it's still Windows 95 or something like that. Because you just have to get back onto it. He had his own companies, also successful. We actually, for a brief time, had a company together. But our innovation would have reduced the cost of assessing cardiac outputs. And that business model in this country falls apart. If you do something that can be done cheap, doctors would not prescribe it, basically. So we couldn't move that on. But he now has Psychometrics as his company. He has had multiple R1s, small business innovation grants. He is a collaborator to many, including the Seidmans, and my work certainly would not have been as successful without him. He is an astute observer of things that are proposed. I remember when Cytokinetics announced omecamtiv, which is sort of an activator of myosin interaction. Brad knew, because he had studied the drug, that explanation is actually not true. FDA didn't also approve it, although the clinical trial showed some benefit. Because he's going to spend 2 nights in Minneapolis, he has to give 2 talks. So this will be a little bit unusual. He gave the first one about myofilament function in LV myocardium of patients with diastolic dysfunction. And then we'll have some, if somebody has questions, we answer the questions. And then we convinced him to talk about his newest innovation, which is basically a myocardial slice device where you can generate force length loops, which are obviously relate to pressure volume loops in patients. So I'm super excited to hear all the new things that Brad has to tell us.
Thank you very much, Marcus. Thank you for that introduction. It's been a real pleasure to visit here again. I haven't been back in the Twin Cities area for about 30 years. It's just been wonderful to visit and to see what's going on here at the University of Minnesota. And it's good to see another friend from Vermont. Steve Bella is visiting. Anyway, it's a real pleasure, and I'm really happy to share with you some of the work that we've done at the University of Vermont. I would like to disclose, as Marcus mentioned, that I'm a majority owner of a preclinical CRO called Psychometrics. Going to be focused on heart failure with preserved ejection fraction. It's a leading cause of morbidity and mortality, and its 5-year survival rate is around 43%. And compared to about 72% of the general population, and it represents about 50% of all heart failure cases. And the prevalence of HFpEF relative to HFrEF is heart failure with reduced ejection fraction. The prevalence of HFpEF is increasing at a rate of 1% per year. And so HFpEF is not benign. That is, the decline in cardiac function, the rate of hospitalization, and the economic costs are similar to HFrEF. And HFpEF is also not a single disease, but a multi-dimensional disorder with a constellation of symptoms and underlying mechanisms. And I like to demonstrate that with this image that was published a few years back. I'm not going to go through every part of this constellation that leads to HFpEF. Some important factors are inflammation, arterial stiffness, and diastolic dysfunction. But each of these contributors consists of multiple underlying causes and multiple molecular mechanisms. So there's an awful lot to study with regards to HFpEF. We are focused on diastolic dysfunction. And in this particular talk and in this particular study, we were interested in the role of the sarcomeric proteins and what role the sarcomeric proteins play in diastolic dysfunction in patients, in human patients that have been diagnosed with HFpEF. So I'm just going to give you a quick reminder of what the sarcomeric proteins are all about. The sarcomeric proteins produce and regulate contractile force. As you see here, if you were to look at a single cardiac myocyte, you see the vertical stripes in that myocyte. Each one of those stripes represents a sarcomere. If you were to look at the sarcomere, a single sarcomere like this, you would find thick filaments and thin filaments, and the proteins myosin and actin are the primary proteins in there. But there are many other proteins in there. There's myosin, titin, myosin binding protein C, and of course there's actin, the troponins, and tropomyosin, many proteins that all make up the myofilaments that are then produce and regulate contractile force. That's just a reminder. If I talk about sarcomeric proteins or if I talk about myofilaments, they're basically the same structures that I'm referring to. So what did we do in this study? In this study, we wanted to compare the myofilament mechanics that we could detect in the laboratory with clinical indicators of diastolic function or dysfunction. So HFpEF, for the clinicians in here, you might recognize the kind of like the score sheet that you would use to diagnose HFpEF in the clinic. But some of the primary factors that would be used to diagnose HFpEF would be an elevated left ventricular pressure in end diastole, a reduced mitral valve ring tissue velocity, or a high early blood velocity relative to E prime. You might also find hypertrophy in these patients, as well as an elevated left atrial dimension and volume in these patients, all surrounding the concept of diastolic dysfunction. So what we did in this study was focused on uncovering any relationship between these clinical factors of HFpEF and the cardiac myofilament mechanics. So let me take you through our study methods. So first of all, the epicardial biopsy samples were taken from patients that were undergoing a coronary artery bypass graft operation. These patients had normal valvular function, normal wall motion, normal ejection fraction, or at least it was above 50%, and they were all scheduled for the CABG. And the patients were then separated. We separated these patients into three groups: the control group, which simply had CAD disease, a HFpEF group, and HFpEF with diabetes. So you'll see somewhere, I'll be noting also HFpEF plus diabetes as the plus DM acronym there. And so the biopsies were demembranated, that is, they were skinned with a detergent so that we had access to the myofilament proteins, and they were sculpted to about 150 micron diameter so that we had good diffusion of calcium into the myofilament spaces. And they were placed, and then these preparations were placed between a length motor and a force transducer so that we could perform a mechanical perturbation if we wanted to these preparations. The myofilaments that mechanics that I'm going to be presenting are the isometric stress versus PCA relationship, and then simple sinusoidal analysis and a quick stretch, which would give us some indication of the myosin kinetics. So I'm going to go through some of the patient characteristics. Now, I'm very sorry I'm showing you this terrific table of results, which is never good to show, but on the right-hand side, you can see basically the summary. That is, these patients were all age-matched. The HFpEF and the HFpEF with diabetes patients were heavier than the controls. These patients had similar levels of beta blocker usage, and the HFpEF patients were on primarily on blood pressure medications. Some other characteristics of the LV in particular, we see that the left ventricular end diastolic pressure was elevated in the HFpEF and HFpEF with diabetes patients. And we have other indicators of wall thickness, for example, and chamber dimension. This also demonstrated that there was left ventricular hypertrophy in the HFpEF patients. Other measures of LV mass, for example, that also demonstrated that there was left ventricular hypertrophy in these HFpEF patients. And then finally, the left atrial dimensions were larger in these patients, that is in the HFpEF. Now, I am very sorry, I just listed at the very bottom that we had a measure of collagen content by mass spec. I was just talking with Marcus earlier this morning. He's not so convinced that was the case. So I think we should try to ignore that very bottom line for the time being, but it really doesn't take away from the bottom message of the myofilament mechanics that I'm going to be presenting. And we also have some echo characteristics. The two primary findings was an increased E wave. This is an elevated early diastolic blood flow velocity, as well as an elevated E over E prime ratios in the HFpEF with diabetes patients. So as a summary, the clinical indicators of diastolic dysfunction included an elevated left ventricular pressure and diastole, the HFpEF and the HFpEF with diabetes. We had LV hypertrophy in those patients. We had an elevated left atrial volume in these patients and an elevated E over E prime ratio at least in the HFpEF with diabetic patients. So what about now the myofilament mechanics? So the first set of mechanics I'm going to present are the isometric stress versus calcium. So this is a situation where we're just going to be measuring force as we increase the calcium activation of the myofilaments. And this represents this graph, this first graph here in the middle represents the stress, that is the force per cross-sectional area of these preparations that is produced with the increase in calcium. As you can see, there's really not much difference among the groups, except at the very lowest calcium concentrations. Now, I'm so sorry, I should have also indicated that all these preparations were stretched to the same sarcomere length, that is 2.2 micron sarcomere length. So they're all starting with the same sarcomere length. But the HFpEF with diabetes patients seem to have a slightly higher stress at these non-activating calcium concentrations. If we were to normalize the stress, that is trying to get an indication of the sensitivity of the force production with calcium, you can see that all of these patient groups show similar responsiveness to the calcium activation. But if we did look at now this lowest stress, this P minimum, or this stress on non-activating calcium concentrations, you see that the HFpEF with diabetes is significantly different from the controls, and the HFpEF patients are somewhere in between. The statistics didn't come out to be significantly different for that set of patients, but this would seem to say that we could conclude from this, or at least this would suggest that the myosin cross bridges are formed with no calcium, or that the myocardium was just stiffer in the HFpEF with diabetes. And so when we stretch it to 2.2, it would just show a higher stress.
I'm curious how well controlled these diabetics were. Is their blood glucose super high, or do you have any experience?
I do have the blood glucose data, and I just can't remember off the top of my head what they were like. Would you remember, Marcus?
They're typically fairly well controlled when they go into bypass surgery. So they are not completely, out of like normative value ranges. Yeah.
And we can characterize the sensitivity to calcium by two factors: the PCA 50, which would be the calcium concentration at 50% activation. You can see that that value is not different among the groups. And then this Hill coefficient, which kind of refers to the slope of that calcium sensitivity. You can see that this Hill coefficient is not different it's not statistically different among the patients. So that was our finding with regards to the isometric stress development and the calcium sensitivity. Now I'm going to present the results from what we call sinusoidal analysis. What we do in sinusoidal analysis is that we take this muscle preparation and we apply a sinusoidal length change to the muscle and record the stress response. Now I'm going to go through what we do with regards to getting this analysis performed. I don't want to dwell too long on it. So if you find yourself getting a little frustrated with my presentation, you can ask me to explain it again, or just wait another couple slides and it'll probably be okay. So what we do is we apply a sinusoidal strain, that is a sinusoidal length change to the muscle, and we record a sinusoidal stress response to that strain. And then we can separate that sinusoidal stress response into two components. One is a component that's in phase with the initial strain, and one that is out of phase or in phase with the velocity of the strain. In those cases, I could use the in-phase component to compare with the original strain, and that will give me an elastic modulus. That tells me how much energy is applied to the muscle and fully recovered. That is, it's elastic. Whereas the viscous modulus refers to the out-of-phase component. That tells me how much energy is completely lost because I'm applying a length perturbation. So this elastic and viscous moduli are what I'm going to be showing you with regards to the frequency of the perturbation. We start at very, very low frequencies of perturbation and go to very high, to like 200 hertz. And we might get a result like this. So here's a result of an elastic modulus against frequency and a viscous modulus against frequency. And you can see it's not just a straight line, it's very curved, and there's all kinds of nuance associated with these. What's important is to realize that the myosin cross bridges have a finite lifetime, and the stress, that is the change in stress that will occur with the change in length, will only happen when the cross bridges are attached. And because of that, we will get a certain signature in these elastic and viscous moduli. More importantly, if you look at the viscous modulus, you'll see a spike in the viscous modulus at a particular frequency that corresponds to the lifetime of the myosin cross bridge. Specifically, the frequency at which you get this peak of the viscous modulus, that frequency we call little c, that frequency corresponds to the average lifetime I'm showing here as T on, the average lifetime of the myosin cross bridge. It corresponds reciprocally. That is, I can calculate the average lifetime of the cross bridge as 1/2 pi c. And in this particular example, you can see that one particular group has a short The normals or the non-transgenic had a short lifetime of around 4 milliseconds, whereas the transgenic mice in this particular occasion, it had a longer lifetime of about 7 milliseconds. Another factor that we can pick out here is the magnitude of that peak. So this magnitude of the peak in the viscous modulus, we call capital C, big C. This peak is proportional to the number of cross bridges. So if we determine that big C, we get the number of cross bridges times the stiffness characteristic. So those are the two values that I'm going to be presenting with relative to these patients. First, I want to remind you what we saw in the previous set of experiments. I'm just going to remind you that we saw an increase in the minimum stress, or that is with no calcium activation, we got an increase in the stress in the HFpEF with diabetics. And the question could be, is this due to myosin cross bridges forming without calcium activation, or is it due to a stiffness of the myocardium? Well, sinusoidal analysis can actually answer this question for us. So these are the results of sinusoidal analysis at PCA7, that is a non-activating calcium concentration. And you can see in the blue, you see that the blue is actually showing these distinct curvatures that indicate that there's some sort of myosin activity going on at this calcium concentration. And we can pick out the little c and the big C, that is the frequency of the peak of the viscous modulus and the magnitude of that peak of the viscous modulus. And I can plot it here. This is the magnitude, big C, and it's probably hard to see there against the PCA value. But at the PCA of 7, that is the non-activating calcium concentration, you can see that there was a higher amount of myosin activity in the HFpEF with diabetes. But there was no difference in these other calcium concentrations. And the 2 pi C, which is the frequency characteristic, that was not different among the groups. So that's an important finding in the sense that this elevated isometric stress without any calcium activation, that is a low calcium, we can still detect that there's some myosin cross-bridge activity, at least in the HFpEFs with diabetes. I'm going to show you the results here. That is, I'm sorry, the results at the top here are the results that we just looked at, but the results down here are at sub-maximal calcium concentrations. And you can see that there's no difference in the myosin activity or kinetics among these groups. So I'm going to move on to another mechanics assay. This is called the quick stretch assay. So it's got the same sort of preparation. So we've got these demembranated myocardium. And what we will do is we will perform a quick stretch of this myocardium. In this case, it's just a 1% stretch. And the force response is shown here. This is an example force or stress response where we would now want to pick out certain characteristics like the peak height or the lowest peak or the recovery peak height of the stress. And likewise, pick out characteristics of the timing. T2, for example, is the time to the lowest trough. T3 is the time to the recovery. But if we were to focus first on the P's, that is the stress that is recorded from this assay, you see that there's no difference among the groups for this assay. And if we were to look at the timing, that also is no difference among these 3 groups. So at least by this assay, we're not picking out any difference in myofilament mechanics among these 3 groups. So I'm going to give you a summary of the comparisons among the 3 groups so far. So the force production, that is the maximum force or the maximum developed force, that was not distinguishable among these three groups. That is the controls, the HFpEF was diabetes. The calcium sensitivity recorded as PCA 50 or as our Hill coefficient, that was also not distinguishable among these groups. What did seem to arise was this elevated relaxed stress that is a higher, we're still not sure if it's a higher passive stiffness, but we do show that there's some myosin cross-bridge activation under relaxed calcium conditions, at least in the HFpEF with diabetes. And the myosin kinetics, as we were detecting by 2πc or by the T2, those were also not distinguishable among the groups that we examined. It was somewhat of a disappointing result. There were tremendous differences in the clinical indicators of these patients, but we weren't seeing tremendous differences in the myofilament mechanics. If we did all of our statistics relative to the groups. But that made us think if we could compare the myofilament mechanics directly to the clinical indicators of diastolic function without regard to the group, without regard to the patient diagnosis. So what we did was we performed correlations between the myofilament mechanics and the clinical indicators of diastolic function. So I'm going to show you first some correlations that we performed with this P-min. This is the minimum stress, no calcium activation. And we found significant correlations for left ventricular pressure and end diastole, a significant positive correlation for E over E prime, as well as a significant positive correlation with LA, that is left atrial dimension. So that's pretty interesting to think that this myofilament characteristic actually seems to be associated with these clinical indicators of diastolic function. I'm going to put those correlations up here in the corner because we're going to be making a list here as we go along. Now, let's look at the correlation with the Hill coefficient. Now, you remember the Hill coefficient is the slope of the calcium sensitivity of force production. Now, we didn't find any differences among the groups if we had the groups separated and did the statistics that way. But we do get a significant negative correlation with left ventricular pressure and end diastole. So that's pretty interesting, and I'm going to put that result up here in my list. Let's look at correlations with big C. This is the amount of myosin that's being activated at non-activating calcium conditions. We find a positive correlation with left ventricular pressure and end diastole, a positive correlation with left ventricular dimension, and with LV mass. So that's pretty interesting too, and I'm going to put those up in my list of correlations. And we're going to go for one more set of correlations, and that is the myosin kinetics. Now, this is myosin kinetics under calcium activation conditions. It's PCA 5.7, which is about middle of the road. It's not maximal, but it's submaximal calcium activation. We find that 2πc, which is the rate of myosin cross-bridge detachment, that is negatively correlated with left ventricular pressure and end diastole. And this T2, which is that's positively correlated with left ventricular pressure and end diastole, as well as positively correlated with E over E prime. So we've got a host of several correlations that are really kind of promising. They really do show that there's something happening at the myofilament level that is at least associated with and could be possibly contributing to clinical indicators of diastolic function or dysfunction. So I'm just going to summarize that. So this elevated force in non-activating calcium could contribute to diastolic dysfunction as measured by these three measures right here, left ventricular end diastolic pressure, for example. The reduced cooperative activation of the thin filament, which is reflected in the Hill coefficient, that could also contribute to diastolic dysfunction. And this elevated myosin cross-bridge formation at non-activating calcium concentrations, that also seems to contribute to diastolic dysfunction and probably underlies the minimum stress that we noted a little bit higher. And then finally, the prolonged lifetime of the myosin cross-bridge could contribute to diastolic dysfunction. These all show up in this patient set if we keep the patients out of their groups and just use the entire cohort as our sample. So I'd like to come to some conclusions with this particular data set. So I think an important finding was that the partial activation of the thin filament, independent of calcium, was associated with and may contribute to diastolic dysfunction. That is the elevated LVP, the elevated E over E prime, and the LV and LA hypertrophy. This would implicate that there's something going on with the regulatory proteins such as tropomyosin or troponins that are affected in the HFpEF and the HFpEF with diabetes. And then finally also that there's a reduced myosin cross-bridge off rate. That is, there's a prolongation of the myosin cross-bridge lifetime at submaximal calcium activation associated with better diastolic function. So this would implicate something going on in the thick filament proteins, such as titin, myosin binding protein C, or the light chains, and most likely post-translational modifications of those proteins. That is the end of my first talk. But if you have any questions about this, I think I should take it now, because the second talk is a completely switch of gears.
Yeah.
Yeah.
How important is the myosin PV's activity for this passive? Did you throw statin or something on there to block that and see if that changes how the passive properties of that level of muscle?
The passive properties, you could absolutely do that. And I'm afraid we didn't do that in this particular set. We normally do that. That is, we would put in, we usually use BDM because we find that to be more reversible. So we might start out with BDM and take a measure of passive characteristics. Now, we've done that on previous studies, and we didn't find a difference between the HFpEF and the controls. And I think that's why we didn't do it this time. And we just decided to keep the BDM completely out of the story, because the BDM is also a phosphatase, and so it could actually affect the phosphorylation status of many proteins, and we just didn't want to do that in this particular study. But I think we have a previous study that did show that. Yeah.
One thing that stuck out to me looking at all your correlations are really driven between the HFpEF with diabetes. That's the outlier. The other two groups seem to really intermingle. What is it that you suppose that diabetes and doing to the myofilament?
I think this might be where you're talking. Like the diabetics are really driving these correlations with big C. Yeah, you're absolutely right. What is diabetes doing? I have no clue. I have no clue. Do you?
No, that's why I asked.
No, I've learned.
Trying to trick you.
No.
I really didn't know.
No, and I really appreciate this, because I had an interesting conversation with Sam Dudley last night about this too, because it really opened my eyes to what diabetes could be doing that I'm just not aware of. And I'm sure there's a lot more to it than just what he was, what we were talking about. But
I mean, clinically, these HFpEF plus diabetes patients don't behave really different that I would see when I have these patients in front of me. What makes me believe that this is actually meaningful is that you found all the clinical variables that we know are meaningful predictors of diastolic dysfunction popped actually up in your basically screening. You know, it's like LV mass, it's E2E prime, it's left atrial size, with the exception of left end-diastolic dimensions. That may be just a coincidence. But the other ones are actually, you know, when I look at echoes, they tend to tell me something about what the substrate is. So that makes me really believe that that this is actually a meaningful finding.
Yes, Joe.
Very interesting. Are these diabetics type 1 or type 2 diabetics?
I think they're all type 2.
Type 2, so they have metabolic syndrome almost certainly, and they might also have hypertension. So that also could be tied in. I had a question about your sinusoidal analysis. I didn't catch the temperature that you used for these experiments.
Everything's at 35 to 37 degrees.
Oh, okay. And I noted that your frequency domain for the sinusoidal oscillations were in the 0 to 100 hertz range. And my memories of this field is that is at the very low end of frequency domain. And to capture, for example, the weakly associated cross bridges, for example, you need to get up to kilohertz or even higher, particularly if you're interested in these weak to strong cross bridge interactions. And it is curious, did you go beyond that, go up to 1,000 hertz or even 10,000 hertz to capture that population across bridge, which has much faster association rate constants?
No, we did not go that high. We went to about 300 hertz, or I had somewhere between 250 and 300 hertz. For the humans, it seems to be fine. I'll have to check on what you're referring to there, but we find that going up to about 300 hertz usually gets us what we want for the human, even at 30, you know, at body temperature. If we were to use mouse or rat or fruit fly, we have to go up to about 1,000 hertz to characterize it.
Thank you.
Yeah.
One more question about your clinical cohort. Maybe this is something Marcus could chime in on too. You indicated that all your patients that undergone have some coronary blockage, which obviously is an interesting point. What I don't know is clinically how many HFpEF patients actually have coronary artery disease as a huge problem, and is there any kind of contribution of ischemia going on here that could affect these findings?
So I think I can answer these questions.
Yeah,
so
please.
ischemia, no, because when we obtained these tissues, we excluded patients who had ischemia in the interior wall. That's where the tissue is taken from. So we're pretty confident that they don't have like overt ischemia. And then for the first part, which was again,
Well, how prevalent is
coronary
artery
disease.
disease in HFpEF patients?
You know, as I tell my HFpEF patients often, as you get older, you get wrinkles. And if you get old enough, you get some coronary disease. And most HFpEF patients have some degree of coronary disease. Typically not enough that they would need bypass surgery, but they are pretty wrinkly. And it's not just that, you know, that's why they have so many other things. That's why they tend to have kidneys that are not the best and like all these other things. It's just that the fact of age accelerated by the presence of hypertension that makes them reset. So it's very common to have coronary disease. It's a little bit more common to have atrial fibrillation because these two diseases go hand in hand. But coronary disease is sort of second in line. Hypertension, they almost all have hypertension. I mean, I'm like 90%. And the remaining 10%, they may have amyloidosis or like a somewhat different disease. Yeah. Any external questions? Okay.
All right, I'm gonna completely switch gears, although it's still cardiac related. But the next 20 minutes is primarily just on methods. I'm not going to be presenting physiology per se, but I'll be presenting methods that are going to be important for examining cardiac physiology. And in particular, it's kind of like the end point here is to demonstrate how we can mimic the pressure-volume relationship using cardiac slices. So I'm just going to show you how you mimic the pressure-volume relationship and demonstrate also that we can get a Frank-Starling response. And we can also demonstrate how we can see diastolic dysfunction in the cardiac slice. So the cardiac slice is a multicellular section of the myocardium. It's usually taken from a transmural block of the heart, and it will be about 5 to 10 millimeters long, about 5 to 10 millimeters wide, and about 100 to 300 microns thick, depending on how you like to slice your slice. But these cardiac slices are very useful because you can now examine signaling and action potential conduction. You can examine gene and protein expression using these slices, and you can also examine post-translational modifications easily due to some sort of perturbation you might perform on the slice. It's also very easy to perform imaging with these slices. I think it's important to note, and I'm sorry I haven't said it already, what you're doing is you're maintaining the extracellular matrix and the myocytes within that extracellular matrix, so that you have a fully functioning piece of tissue in the architecture that it was in vivo. So in many ways, you're studying the individual myocytes, but in their natural environment. You can also do some longitudinal studies. You can incubate these cardiac slices for quite a long time. We've been successful out to about a week, but we stopped after about a week because we just didn't have a project for longer incubation periods. But there are other groups that incubate for months.
The force frequency that you show there, is that like room temperature or like?
Oh, I don't know. This is just,
Because it's like, if it's rodents, that's surprising. In strips, it's usually negative. Yeah.
So I say I adapted, but I actually stole. I stole that image from Watson et al. You can also load these slices with fluorescent dyes so you can get a measure of intracellular calcium handling and action potential, and you can measure contraction relaxation function. And as I'm going to demonstrate to you, you can perform force length work loops. So I would like to show you, I'm going to show you a video of how these cardiac slices are prepared. I've got two videos and they're both short. This is just 1 minute long. Am I able to start the video?
To turn off your laser first.
That's okay. I mean, we're going to live without it. It'll be just fine. If I get out of presentation mode.
Did I go too
No,
far?
a little further, just a little further. Just a little further. Right about there. Yes, there we go.
You gotta stay out of the.
Sorry, guys. Sorry, guys. Where?
Oh, I think, yeah. It showed up there for a second. Hey, very good. So that was. At first you saw a left ventricle of a rat, and we had taken off the atria, we had taken off the right ventricle, and we had cut all the way down from the base to the apex. And now I'm placing that left ventricle onto a glued surface, and that surface, the glue just keeps the epicardium down, so the endocardium is up. Then we can fill up the bath with a relaxing solution. You can see we can keep the solution oxygenated, and then we just have a razor blade come and slice slice the heart. So you get these slices, you can dictate just how thick you like to have your slice. This is a more modern one. The previous one I was showing you was an older model of vibratome. This is a newer model of vibratome, which we tend to use now. And it's a little easier to work with, and you get nicer slices. But what happens is that razor blade will go back and forth at about 80 hertz and just move forward very slowly, and it makes your slice. We'll see if I can do it again.
And you always go from endocardium to epicardium,
Yes.
because I mean, the two, the epi versus endo behave actually quite different.
Yes.
And you see that when we
Yes,
compare the slices.
we do compare
Oh,
and we do see it.
Yeah.
Let's try this again. I think I got it.
I think so. This.
No, I think it's going.
Oh, that's going. Okay.
So I'm going to show you how to put the acrylic clips onto the slice. Oh, I've gone way too fast here, but anyway, I really was hoping I could pause. I'm not going to bother pausing. But this is a cardiac slice, and what we do is after you've figured out which orientation your filaments are in, you can now use a razor blade to cut your slice into a rectangular dimension so that you've got the filaments going in one particular direction. Now, I put some glue on the end of that clip, put some glue on the other end of the other clip, and just drop that on. And I mean, this is at like twice the speed, but it really takes very little time
You
to.
say glue, Brad, you mean like a mild pack, or what do you?
No, it's like a super glue. Or
Just the water activated super glue?
that's right.
Are you taking an oxygen while you're doing this?
That part during the gluing, of course, I can't keep it oxygenated then, but it's just fine. It seems to be quite robust. And it'll, yeah, and you can see now I'm loading it into the device like that, and then I can just stretch. After getting it onto the.
And you're
onto
still
the
in
device.
PDM titles.
Here I was, there, no.
Okay.
What we usually do now is I have a second step where I rinse out the BDM and then I put it into the chamber. I think that's it.
And
So-
then you apply preload to LMAX, so what do you use?
Yeah, so let me move on. So what we can do is we can detect sarcomeres. If we cut the slice thin enough, usually less than 250 microns, then you can visualize the sarcomeres. I've gotten to the point where I like to use about 125 microns, so I can visualize the sarcomeres every time in almost the entire slice. So I feel comfortable with that. And as Marcus said, now we can set the preload. Either what I do now is I set the preload as a sarcomere length, but you can set it using any other way that you might like to do it. But I use sarcomere length to do that. Now, many of you are probably used to using single cardiac myocytes. You might measure the shortening dynamics. But in this sort of preparation, we're going to be using the force transducer, which is on the left-hand side, to record the contractile characteristics of the cardiac slice.
Is that the Guth transducer?
Yes, it is. He's referring to Conrad Guth, who is a pioneer in muscle mechanics. He gave me the design.
Oh, really?
Yeah, so I make them in my basement now. I shouldn't say he gave them, I paid him.
Yeah.
But Conrad has since passed away. He
Yeah.
passed away a few years back, but he was a real pioneer in the field.
But he worked in the field.
Anyway, so we can measure the contractile dynamics of these cardiac slices. And I put a little arrow there on the right-hand side because we can mimic the cardiac cycle if we can control the motor. There's a motor on the right-hand side of the slice. And so what we do is we monitor the force on the left-hand side and control the motor on the right-hand side. So we can now start to mimic a cardiac cycle. So just for those of you who haven't taken your cardiac physiology recently, this is thanks to Marcus for this.
I stole it somewhere, it's online.
Well, thanks for stealing it for me. But just to remind you what the cardiac cycle looks like in terms of pressure and volume, the relationship, that pressure and volume can be mimicked to some degree in the cardiac slice. So what I'm showing you on the right-hand side, oops. So this is, you can see a cardiac slice there undergoing a cardiac cycle. So what's happening is the force is being developed while the cardiac slice is held isometric. So there's no change in length until it reaches a particular afterload that has been preset. And once that force reaches that afterload, the motor allows the muscle to shorten. So this is the muscle length over here. The muscle is now shortening at the very top of the force transient. And then there's an isovolumic relaxation phase where the force is now falling, but there's no change in length until finally it gets down to a pre-specified diastolic force or preload, and now the muscle is allowed to re-lengthen again. This is the look of a normal in vivo pressure volume relationship with left ventricular volume on the bottom, left ventricular pressure on the y-axis. That is mimicked in the cardiac slice. It looks something like this, where we can set the preload and the afterload as indicated here. Now, you might set preload by sarcomere length, or you can set your starting preload at sarcomere length. The computer program uses, however, the actual force at that starting sarcomere length. So it uses the force so it can perform the force feedback that creates the cardiac cycle.
These are contractions that are just driven by stretching, or?
No, these are contractions that are initiated by an electrical stimulation.
Okay, so you-
Right. I'm sorry I didn't show that. I should have pointed that out, but you can see the electrodes. There are field electrodes right there inside the chamber.
The electrodes are synced to the motors. That move.
The other way around, the electrodes or the contraction is kind of, I'm sorry, the electrical impulse is sort of like the sink. Everything else syncs to it, the electrical
I
stimulation.
guess what I'm trying to ask you, Fantastic.
Right. What's also kind of handy is that we can also mimic an atrial kick. So we can set the preload in such a way that it allows for the mimicry of a diastasis. That is, there's a portion of diastole where there's usually in vivo, there's not much volume change. And so we can mimic that diastasis, and then we can mimic the atrial kick. That is the amount of inflow of blood that comes with the contraction of the left atrium. So you can see here, this is the E wave and the A wave you would get across the mitral valve. That is the early and the late blood flow across the mitral valve in diastole. And we can mimic that in the cardiac slice here. This is a real, this is data from a real cardiac slice where we're mimicking now the E wave and the A wave. That is the early and the late filling phases of diastole. All right, and now I can also just want to demonstrate that we can change afterload and we can change preload. So with changes in afterload, the shortening will be controlled to maintain the afterload. So if we used a fixed afterload, as we do here, you can see I get more shortening with lower afterload. I can also change preload by changing the sarcomere length. So in this case, I'm only changing the preload by increasing the sarcomere length about 1%. And with that, I can now show you the pressure-volume relationship for all four of those conditions. And you can see that we get a nice end-systolic force length relationship that mimics the end-systolic pressure-volume relationship. And likewise, on this diastolic side, the end diastolic force length relationship that mimics the end diastolic pressure-volume relationship.
Have you tried this on stiffer myocardium? Does it get more exponential?
It's funny you say that.
Oh, sorry.
I'm just good. I think this is my last slide or second to last slide, just to show an example of a wild type versus a C protein knockout. The C protein knockout has a very stiff myocardium and almost no Frank Starling response. So you can see in the wild type, I get the Frank Starling response. I get my end systolic PVR relationship is steeper than the end diastolic PVR relationship. But in this mouse, this is a cardiomyopathic mouse that has almost no Frank Starling relationship. So you can see that the end systolic and end diastolic relationships are nearly parallel. And this also shows that the end diastolic relationship is stiffer or steeper in this mouse, which has a lot of fibrosis. If you were to look at these parts, you see a lot of fibrosis, and they're known to have stiffer myocardium in diastole. So anyway, that's just a demonstration. Like I said, I'm not really, even though this is a nice result, it's just a nice demonstration of the methodology that we're now using in our laboratory to examine diastolic dysfunction. I'd be very happy to take any questions you might have. Yeah. I think theoretically you could reuse the clips, but there's really no point. I mean, they cost pennies, and so you may as well just throw them away. What we tend to do is we also, I mean, I was showing you acrylic clips that are about they're about 500 microns thick. We've been toying with that a little bit more. Now we use Delrin clips that are only about 200 microns thick, and we laser cut them. And so we've tried all kinds of different designs now too. So we've tried different designs that make it easier to mount or easier to glue And so I'm just showing you one set of examples, but the clips are really, really cheap and we just laser cut them ourselves.
Medics are still really slow. If you think is the problem there, and you're like Brad Hart speaking at 3 hertz or whatever.
These results, I think were at room temperature. So I think that's why it's slow. What we generally do now is we will run at about 35 degrees, between 30 and 35 degrees, and then everything's at, so our frequency is of contraction is closer to 3 or 4 hertz.
Driving faster?
Oh yeah, you can drive it up to 6 if you wanted to, right? I think say that again.
What happens? Frequently you place them at, you know, 10 and 7 hertz, somewhere in that.
Well, eventually the diastolic force will rise because it will never fully relax. That's true. I haven't seen that at 35 degrees, but I've never gone higher than 6 hertz.
So your towers, their isomorphic relaxation, does that match what you see in vivo, or is there?
I haven't made that. Yeah, I haven't made that comparison. To some degree, I've just been working on the technology, not really. I'm only just now starting to get to these sort of really important physiological questions. Those are really important questions. That's true. And I'm so sorry. I don't have the answer.
But if you do want an answer, Julie and I just purchased this system and it will be available pretty close to the Marcus Meyer.
No. It's like,
Right now, you're just showing the anti-diastolic force length relationship as linear, but it's really not. It's sort of fixed.
Right, right.
Because it's just the end point of the loop, that right lower corner point, and even sort of clinicians who have done this often get this wrong. They take the whole diastolic filling and say, "Oh, this is all part of the diastolic pressure volume relationship." It's for that curve. That's really not true. It's really the corner point. So, you know, it should end up to,
Right.
if it's really like the pressure volume relationship, it's sort of like,
Right.
it goes like this.
That's a good point. I'm sure it will be. I mean, all of this biological material gets stiffer the more and more you stretch
Exactly.
it. So it's going to have a
Yeah.
non-linear stiffness.
Yeah.
It's just getting stiffer and stiffer.
And you have a microscope sitting below this.
Mhm.
Have you done like Fura just looking at calcium trend?
Oh yeah, I'm so sorry I didn't demonstrate to you, but we can indeed measure calcium regulation. We get better luck using Cal-Red rather than using Fura, but you can still use Fura. Cal-Red is another ratiometric dye, so it's very similar in how you interpret it, but we just have better luck with that because one of the issues that you will have is motion artifact, and we seem to do better with less motion artifact using the Cal-Red as opposed to the Fura.
And like Fluo4, we tried that.
Yes, Fluo4 works just fine too, but that has
such a nice yield.
yes, but it's not ratiometric, and
Yeah.
so some people would argue that it's really prone to the motion artifact.
Okay. Very cool. Any other questions? Well, thanks for your.
I appreciate it. Thank you so much.
It was actually us asking for the conversion. Yeah.